Hello, I am Joshua Brackenseek. I am here to present two papers. The first is Generalized GM MDS, Polynomial Codes or Higher Order MDS. The second paper is AG Codes Achieve List Decoding Capacity over Constant-Sized Fields. These papers are joint work with Manik Dar, Sivkanth Gopi, and Zihan Zhang. To start, we will go over the necessary background to understand the main results and then present the main results. Then, we will discuss the first paper, Polynomial Codes or Higher Order MDS. Then, we will discuss the second paper by looking at what are known as relaxed higher order MDS codes and their applications to list decoding. Finally, we will conclude the talk and give some open questions. In this talk, when we refer to a code, we mean a linear code, that is, a k-dimensional subspace of f to the n, where f is a finite field. We can think of C as a way of taking a message on k symbols and transforming it into a message on n symbols with redundancy. The most common way to represent a linear code is by a generator matrix. The rows of the generator matrix form a basis of C, so it is a k by n matrix. Dual to the generator matrix is the parity check matrix, where the rows of this matrix form the basis of the dual code. Another way to think of the parity check matrix is that its right null space is the original code. An important family of codes are maximum distance separable codes. The well-known singleton bound says that the distance of the code, that is, the minimum Hamming distance between any two distinct code words, is at most n minus k plus 1. We say that our code is MDS if we achieve equality. In particular, the distance is exactly n minus k plus 1. MDS codes have many important properties, including having optimal, unique decoding for substitution and erasure errors. There are also many other equivalent formulations of what it means to be an MDS code, including that every k columns of the generator matrix are linearly independent. Let's now discuss an important example, Reed-Solomon codes. In a Reed-Solomon code, we pick n distinct points, alpha 1 for alpha n, in our field f, so the size of our field has to be at least n. The rows of our Reed-Solomon code are first a row of all ones, then a row of alpha 1 to the 1 to alpha n to the 1, then alpha 1 squared to alpha n squared, and so forth. This turns out to be an MDS code, and in fact, in a very recent line of work, if you pick these generators randomly, they can also more or less perfectly do list decoding. We'll discuss the ingredients for proving these results and building off of them soon. In particular, in order to understand things like list decoding for MDS codes, we need to realize that only some MDS codes have these properties, including achieving list decoding capacity. Another property is realizing all generic zero patterns related to the GM MDS theorem, which we'll explain soon, as well as having optimal recoverability guarantees in distributed storage. The notion of higher order MDS codes abstracts these properties, as we shall see. As our first example of a higher order MDS code, let's look at list decoding. We have a code C in a space f to the n of dimension k. We let its rate be the ratio of k to n. We have x be some point in our space, and we let rho be a radius between 0 and 1 minus r. The goal is to find all code words which are within a short distance of x, in particular a distance of rho times n. We say that our code is capacity achieving if when we pick rho to be very close to 1 minus r, the list size is still constant. An important definition of a higher order MDS code by Roth says that if our code is LD-MDSL, if for any distinct code words C1 for CL plus 1 and C, we have that the sum of the distances from x to these CIs are at least L times 1 minus r times n. In particular, this implies that your code achieves average radius list decoding capacity as long as L is approximately 1 over epsilon. We now discuss a different interpretation of higher order MDS codes. We're going to have G be our generator matrix and let its columns be G1 for Gn. Given any combinatorial subset A of 1 for n, we let G sub A be the span of the corresponding column vectors. With this definition, we can say that a code is MDS if G sub A is equal to f to the k whenever the size of A is at least k. Myself, Gopi, and Makam, building off of this, made a notion of higher order MDS codes. In particular, were MDSL if for any L subsets A1 for AL, the dimension of GA1 for GAL, when you intersect them, is equal to the dimension of WA1 intersect for WAL, where W is a generic matrix. You can think of a generic matrix as the entries of W being randomly sampled from a very large field. What's been shown is that the notion presented on the previous slide and this notion are equivalent up to duality. In particular, if you can construct a good code for one, you can construct a good code for the other. Another connection with higher order MDS codes is the GM MDS theorem. The GM MDS theorem studies what are known as zero patterns. When you pick a generator matrix for your code, you have some freedom because there are many possible bases for the same code. In particular, based on how you pick the generators, you can have certain entries in your matrix be zero. This is known as a zero pattern. It's been known for a while for a random linear code what are all the possible zero patterns. What was recently shown in the GM-MDS theorem is that a Reed-Solomon code can attain the same zero patterns. In particular, for any given zero pattern, you can attain it over a small field size. Perhaps even more surprising is that these notions of higher order MDS codes are in fact related to these generic zero patterns. In particular, MDSL is equivalent to being able for your code to attain every generic zero pattern of order L, where by the order we just mean the number of distinct rows in the zero pattern. As a result, by going through the GM-MDS theorem for this higher order MDS framework, we're able to show that generic Reed-Solomon codes are MDSL, and in fact they achieve list decoding capacity. However, this is only over exponentially large fields. Later works were able to reduce this down. The main takeaway here is that higher order MDS codes unify many different parts of coding theory, and so they are a fundamental object in the study of many of these problems. What we want to ask today are two questions. One, which families of codes are higher order MDS? Can we extend it beyond things like Reed-Solomon codes? The second question is, can we use these higher order MDS codes to construct list decoding capacity achieving codes over small fields? So the problem is there are lower bounds known for these codes that they need exponential field size. So if we can reduce the field size, we can still perhaps achieve list decoding capacity, just not higher order MDS, which is a stronger notion. Let's now discuss the main results. In our first paper, Generalized GM MDS, Polynomial Codes are Higher Order MDS, we show that over exponentially large fields, what are known as random polynomial codes are higher order MDS. In our second paper, AG codes achieve list decoding capacity over constant size fields, we generalize higher order MDS codes to a notion of relaxed higher order MDS codes. And we show that over small fields, random polynomial codes are this relaxed higher order MDS, and the proof uses the results from 1 in order to prove this. As a corollary, this means that AG codes themselves actually achieve list decoding capacity over constant size fields. We now compare our main results to some of the previous works in the literature. So in particular for nonlinear codes, linear codes, and Reed-Solomon codes, we now know very good capacity achieving bounds for these codes, and in fact the field sizes are essentially optimal. For AG codes, it's been known that you can get constant field sizes, but you have to modify the code in a nonlinear way. Our main results are for a random polynomial code, you can achieve capacity, however you need an exponentially large field. But for random AG codes, we're able to reduce the size to a constant size and maintaining the linearity of the code. That concludes the discussion of the main results. Now we discuss the first paper, Polynomial Codes or Higher Order MDS. Let's now define a polynomial code. We are going to take k polynomials f1 through fk that are linearly independent. We're also going to have generators alpha1 through alpha n in our field. And each row of the code is just going to take each of f1 through fk and evaluate it at all endpoints of the code. In our main result, we showed that for a random choice of these alphas, the corresponding polynomial code and its dual are MDSL, as long as the field size is exponential. And in fact, this exponential field size is optimal due to a known lower bound. A key observation in the proof is that it suffices to consider monomial codes, that is, the case where each polynomial is just a distinct power of x. Note that Reed-Solomon codes are captured in the case that each ai is equal to I minus 1. If we let G be a generator matrix of the polynomial code, it suffices to prove that the intersections of the dimensions is 0 whenever it generically should be. To prove this fact, we use an induction similar to the GM MDS theorem for Reed-Solomon codes, and in particular, in order to abstract their techniques for Reed-Solomon codes, we come up with what are known as MDS codes with a basis, where in addition to the code, we keep track of a basis of vectors. And this is important for porting their inductive approach to our setting. We also extend our main result from polynomial codes to varieties. A variety is a solution set to a system of polynomial equations. It is an implicit characterization of the set of points instead of an explicit characterization. We say that our variety is MDS if it is not contained in a codimension 1 hyperplane. From this MDS variety, we can build a code by sampling n points from X as the columns of a generator matrix. In particular, we need the MDS condition so that the rows are linearly independent. What we show is that if the variety is irreducible and sufficiently large, then a randomly sampled variety code and its dual are higher order MDS. Irreducible here means that the variety can't be split up into multiple pieces. This result will be important when discussing AG codes. That concludes our discussion of the first paper. Now we will discuss the second paper, and in particular discuss relaxed higher order MDS codes and their applications to list decoding. We will now redefine what it means to be a higher order MDS code. In particular, given a generator matrix, we say that it is MDSL if for any generic matrix of the same shape, and for any A1 through AL, if the intersection of WA1 through WAL has dimension 0, then the corresponding intersection in G is also 0. This ends up being equivalent to the other definitions discussed earlier. We can relax this a bit with what we call a lower relaxation. There's also an upper relaxation we define, but that's not important for this talk. Here, we let W be a generic k minus d times n matrix. So d is some parameter, and so we're making W have less rows. What we're now going to do is look for any A1 through AL of size at most k minus d, and look again at this WA1 through WAL. Since W is smaller, it ends up being harder for the intersection to be 0. So this is in some sense less conditions to check, so it's a relaxation. What we want is whenever this is equal to 0 in this smaller dimension, then G in the bigger dimension is also equal to 0. The intuition here is that an n, k relaxed MDS code with parameters D and L looks like an n, k minus d MDSL code. There's also a natural definition in the list decoding space of a relaxation. It's actually very straightforward. What you just take is the radius from before of L over L plus 1 times n minus k over n, and decrease it by d, so n minus k minus d over n times L over L plus 1. And this is going to be our average radius list decodable radius. Note that in this list decoding definition, if we let d be approximately epsilon times n, then even with this amount of relaxation, our code is still capacity achieving. So again, here's the two definitions, the lower relaxation and the LD-MDS relaxation. And what we show is that these are essentially equivalent, up to duality. For any relaxation parameter d, if you relax the RLD-MDS notion, then its dual is a relaxed higher order MDS code in the lower relaxation definition. And the proof of this is very similar to the proof for in the case of normal higher order MDS codes, and in fact you recover it with the parameter choice of d equal to 0. Now let's go back to variety codes. So we're going to pick some variety, which is MDS, and we're going to look at a bigger space than just our finite field f. We're going to actually look at the algebraic closure, which is infinite. So we have a variety over this algebraic closure to the k. And we're going to define pxl to be the maximum number of zeros, a degree L polynomial, generically non-vanishing on x, so most points on x do not vanish. We want to look at the maximum number of points over x intersect f to the k. So we have it not vanishing over the whole space, but we're going to look at how many zeros there are over the small space. And what we show is that if this px comma l parameter is small, but x intersect f to the k is big, so basically it's a large variety, then we end up getting, with high probability, a random code of this sort is a good list decoder. This proof adapts the previous proofs for Reed-Solomon codes, although it generalizes it significantly. Note that a necessary ingredient in this proof is that these variety codes are higher order MDS. In particular, we need the results of the first paper in order to prove this result. For our application to algebraic geometry codes, what we do is we just pick our variety x to correspond to a well-known AG code, in particular the Garcia-Stichanoff tower. And we pick our field size to be p squared, and it turns out that x intersect our space is approximately linear, whereas our maximum degree is roughly constant. As a result, we showed that if our field size is exponential, then for sufficiently large n, a random n, k AG code will be this relaxed higher order MDS code with high probability, in particular its capacity achieving. And this concludes the discussion of the main results of the paper. So now let's recap and discuss some open questions. First, higher order MDS codes generalize MDS codes and have many applications, as we've seen from list decoding to other problems. For exponential field sizes, arbitrary polynomial codes are higher order MDS. In particular, they have many nice properties as a result. For smaller field sizes, we can relax the notion of higher order MDS and show that these polynomial codes are relaxed higher order MDS. In particular, for algebraic geometry codes, we get list decoding, capacity achieving codes with constant field size. So now let's discuss a few open questions. One is, can we show even broader classes of algebraic codes or relaxed higher order MDS? For instance, something like this was studied in the case of polynomial ideal codes by Ranzui, Venkatesh, and Wouters. They were able to generalize things like folded Reed-Solomon codes and give codes which have explicit list decoding algorithms, although the codes are technically not linear. Another important question is, let's say I give you a code with high distance. In particular, the code is very good at unique decoding. If we randomly puncture the code, does this also achieve list decoding capacity? I think this would be a very interesting problem to resolve, and it's only known in some special cases. Another very interesting question is to resolve a field size gap. In particular, for both random linear codes and AG codes, we can get capacity achieving codes over a field size of exponential and 1 over epsilon squared, but the best lower bound is 1 over epsilon. It seems like some very hard problems in combinatorics would need to be solved in order to close this gap. Thank you very much for coming to this talk. This illustration just shows the difference on the left between an MDS3 code and a code on the right that's not MDS3, because the three subspaces shown by the dashed lines intersect. Thank you.